The Tungaska object's true identity, what we now know about the 1908 explosion. On February 15, 2013, at 9:22 a.m. local time, a 20-meter asteroid entered the atmosphere over Chelyabinsk, Russia, and exploded at an altitude of approximately 30 kilometers with the energy equivalent to about 500 kilotons of TNT, approximately 30 Hiroshima bombs. The shockwave shattered windows in 6 Russian cities, collapsing part of a zinc factory roof. Over 500 people were injured, primarily from broken glass. The event was captured on video by dozens of dashboard cameras, creating the most thoroughly documented meteor event in history. And crucially, it was exactly the kind of event, an airburst by a relatively small stony asteroid, that Tunguska had been. The Chelyabinsk event gave scientists something they had never had before: detailed instrumental data from a comparable airburst. Seismic networks, infrasound detectors, satellite instruments, and surface cameras all recorded the event simultaneously. The data allowed scientists to precisely characterize the Chelyabinsk meteor's size, composition, entry angle, speed, and the atmospheric behavior that led to the airburst. Applying the same analytical framework backward to the historical records of the Tunguska event, scientists could significantly refine their understanding of Tunguska's object properties. The Chelyabinsk comparison confirmed that the Tunguska object was almost certainly a stony asteroid rather than a comet, an iron meteorite, or anything more exotic. Stony asteroids fragment explosively in the atmosphere at approximately 50 times the pressure they can withstand on the surface. For the Chelyabinsk 20-meter asteroid, fragmentation occurred at 30 kilometers. For a 50-80-meter object like Tunguska, at a steeper entry angle and higher velocity, fragmentation would occur lower, at the 5-10-kilometer altitude consistent with the observed blast pattern on the ground. The comet theory was effectively ruled out. Comets fragment much earlier and more gently. The most sobering finding from the Chelyabinsk analysis was the demonstration of how little warning we would have had. The Chelyabinsk meteor came from the direction of the sun, making it impossible to detect with ground-based telescopes. It was not detected by any early warning system before it entered the atmosphere. For a 20-meter object, this is somewhat acceptable. At that size, the damage is significant but localized. For a Tunguska-scale 50-80-meter object, arriving undetected could result in an airburst over a populated area with no warning of any kind. Planetary defense against Tunguska-scale objects in the 50-150-meter range, is now recognized as the most pressing category of asteroid impact risk. Objects larger than 1 kilometer are tracked well enough that we would have years of warning before impact. Objects below 10 meters typically burn up in the atmosphere. The 50-150-meter range, large enough to destroy a city but small enough to evade detection until close approach, is the most dangerous gap in our detection capability. An estimated 25,000 to 100,000 such objects exist in Earth-crossing orbits, and we have cataloged only a small fraction of them. The probability of a Tunguska-scale event over a major city is low but not negligible on a geological timescale. Events of Tunguska's size occur approximately once every 500 to 1,000 years. The Earth's surface is mostly ocean and uninhabited land, so the probability of a given event striking a populated area is relatively low. But with 8 billion people on Earth and the growing concentration in urban areas, the expected damage from a Tunguska-scale urban airburst would be catastrophic, potentially millions of casualties, if no warning were available. Planetary defense efforts have accelerated since Chelyabinsk. NASA established the Planetary Defense Coordination Office in 2016. The European Space Agency has a similar program. The Double Asteroid Redirection Test, DART, spacecraft was deliberately crashed into the asteroid Dimorphos in 2022 to test whether kinetic impact could deflect an asteroid. It worked. Dimorphos's orbit was changed by a measurable amount. The technology to deflect an asteroid, given sufficient warning, now exists. The remaining challenge is the warning, detecting the right object soon enough to act. June 30th, 1908. Something hit the atmosphere over Siberia and no one was there to see it. On February 15, 2013, something similar hit the atmosphere over Chelyabinsk and thousands of dashboard cameras watched. The 2013 event gave us the data to understand the 1908 one, and together they tell us something important. This happens. Not often enough to be a constant threat, but often enough that it will happen again. The question is not whether something of this size will hit the atmosphere again. The question is whether we will see it coming and whether we will be ready. The answer right now is sometimes, and sometimes is not good enough.